plus tons of community service, plus you have to show that you help out in your parents' shop, plus a whole bunch of stuff. So I'm just curious, GPA to get into Berkeley. I think that a lot of this is not shown because it's above the 4.0 line. Okay, the blue and the green represent accepted students, so you can see that the great majority of students who got into Berkeley have a GPA above 3.5. They can probably bump this number up to like 4.4. Anyway, so here's the question. Why is it possible to transfer to Berkeley with a different type of GPA? Nobody has the answer? Okay, the question is, to get into Berkeley, or even UC Davis, to get into UC Davis as a freshman from high school, you still need a pretty good GPA to get into UC Davis, which is not even in the same league as Berkeley, right? But to transfer to Davis, I think the GPA is what? 3.2, 3.3, maybe 3.5, but it's not quite the same GPA as from high school. So the question is why? Well, first of all, why do they accept transfer students?
Proven.
Huh?
People drop out.
People drop out. Very good. So some people paid a lot of money for the first 2 years at Berkeley, UC Davis, and some of the other four-year universities, and they drop out. Why do you think these people drop out? Remember, these people got in with a 4+ GPA to begin with. So we are not talking about people who are unmotivated or who are underperforming to begin with. Yep.
I guess it's a big difference.
I think that might be part of the reason, but I don't think that's the majority of the reason. I think people, when they study for high school, it's a different way of preparing for college classes. So when you take an exam in a college, even in this class or other classes that you're taking here, what you need to do is different from high school, or at least it's different by enough that some people who could really do well in high school find it difficult to do well in college. And then plus you don't have the parents on campus saying, hey, you're supposed to do this, go to bed early and stuff like that. So I think some people just decided to do things on their own, and did not turn out to be optimal. So anyway, that was just a curiosity thing that I asked. All right, so we're going to finish up trees today, and I'm not remembering how far we went through. I distinctly remember that we went through depth first search. So we performed the pre-operation before we do anything else. And then for each child of a particular vertex, we will perform the recursive call between two children, but only between the children. We'll do a mid operation, and then we'll do a post operation. Pretty sure we talked about this already, and I gave you guys a list of these operations based on a particular tree. And I made one mistake. I forgot one of the mid operations, and somebody helped me correct it and go like, hey, we're missing something here. So that is absolutely correct. So the next question is, why is this useful? Why do we want to be able to traverse trees? I also remember that I used a tree to represent an expression, and we traversed it in two different ways, using either the pre-operation or the post-operation, and then we ended up with a prefix notation and a postfix notation, depending on what we do with the pre, mid, and post operations. Do you guys still kind of vaguely remember that? Okay. So here's the next question, which is even more practical. You can represent every single program that you write in C, C++, Perl, PHP, and etc. as a tree. Okay. So that's a given fact. So why do you think tree traversal is also useful in the context of a compiler? What are you actually doing with the pre, the mid, and the post when you are parsing a particular program? What is the compiler? What does the compiler do?
First, I don't like it.
Into some way that a computer can execute, right? Into some form that a computer can execute. So if you're dealing with a compiled language like C and C++, it does translate that into machine code or assembly code. If you're dealing with a scripting language or a interpreted language like Perl, PHP, or Python, it will store it internally into some kind of representation, and as it needs to, it will go through those representation and execute the code accordingly. But in the context of a compiler, which has to translate a high-level program into assembly code, why do you think tree traversal may be an important concept in such a compiler? It's easy, by the way. It is easy to turn a C expression into a tree format. That is actually pretty easy. But once you turn it into a tree representation, it's still not in machine code or assembly code. So how do you generate assembly code from a tree representation of a statement? Well, think about it. Just think about it a little bit. Let's talk about a while loop. Okay, so with a while loop, we have, it has a general format like this, right? The placeholders, the important parts are not the while keyword. Okay, so once this is compiled, the while keyword is gone because the only purpose of the while keyword is to signify this is a pre-checking loop and this is the beginning. So that means, the while word itself, the keyword, has no particular meaning when it comes to the tree representation. What it really boils down to is really just the condition and the statement. Okay? So you have a very simple tree in this case. You have a condition, you have a while loop, which is the root here, you have a condition, and then you have a statement to perform here, and this is your tree. Okay? But the tree is oversimplified because the condition itself is a tree on its own. Okay? It is some kind of expression that evaluates to either 0 or non-zero. The statement can be a huge tree as well, depending on what is in the body of a loop. Is that okay so far? So when you're traversing a tree like this, and your objective is to generate the code to make this happen in assembly code, what are you doing with the pre, the mid, and the post operations? Well, the first thing you do with the pre is you create a label. Okay, so you know where to go back to at the end of the loop. Is that making any sense? And then you generate the code for the condition. And when you want to generate the condition, you want to generate code not for the condition itself, but the negation of the condition. If the negation of the condition is true, you go to the end label to get out of the loop. And then you generate code for the statement. But who's going to generate code for the statement? Well, that's the responsibility of another recursive call of this algorithm. Okay, so you just call the algorithm recursively and say, hey, generate code for the statement. The statement can be another while loop, can be a conditional statement, can be whatever. It doesn't matter. When this code is all generated, what do you do with the post of the while loop? Jump back and also make a label for the exit point of the loop. Okay? So these are the practical use of trees and also the traversal algorithm. Are there any questions about this example? No particular questions about this example? Okay. I just want to give you these examples so that it will help you understand, well, first of all, the importance of trees, and two, what we are actually doing with the pre, the mid, and the post operations. All right. And I think that is all for this part. Okay, so we are now moving on to this part here, which is something that we have not talked about. We all talk about the inner child of people, but in graphs they don't have an inner child, but they have an inner tree. Okay, so most graphs have an inner tree. In this case, we call those spanning trees. This is a hyperlink to bring you to a Wikipedia page, but I can describe it pretty easily here. A spanning tree is a tree in a graph. In other words, if T is VT, ET, okay, in other words, it has a set of VT as vertices and ET as edges, is a spanning tree. If T is a spanning tree of G, then they have to have exactly the same set of vertices. In other words, a spanning tree of a graph will consist of exactly the same vertices. But the edges is really just a subset. It can be a proper subset, but it can also be exactly the same as the original set. So when you look at the set of all the edges in a spanning tree of a graph, it is a subset, not necessarily a proper subset, but it is just a subset of all the edges in the original graph. And T otherwise has all the properties of a tree. Okay, remind me again, what is the most important property of a tree that makes it not the same as a general graph?
Root?
Well, there's a root, okay, you can pick out the root, but what else?
There's only one edge to connect to the leaves.
Okay, which is another way to say that is there's only one way to get to any vertex in a tree. Okay, very good. In some cases, a graph cannot be spanned by a single tree, which means some of the vertices are not connected. In this case, the spanning you have to use a spanning forest in order to connect all the vertices. A forest is a set of trees. And I did not invent this term. Okay, the term forest is not colloquial or some joke that I think of. It is actually a technical term. Okay, a forest is a set of trees in computer science. Yeah, I know you guys think well, maybe Tech just came up with this one. No, I did not. So we'll talk about what a spanning tree is and why it is important. A spanning tree is important because it is a way to connect all the vertices in a graph and still maintain and have the properties of a tree. Now, tree is nice in many ways because it has no cycles. There's no way you can run in circles in a tree. There are no two ways to get to the same vertex, and then you can reuse all the algorithms that we can use on trees, and they are in general simpler compared to graph algorithms. And there are applications of spanning trees. This one is not a Wikipedia page. It is actually something else. The website is called Geeks for Geeks, okay? And it turned out to be a pretty interesting website. It has a lot of useful articles. So I'm just going to go through some of the applications of what we call a minimum spanning tree, or MST to be short. This is a graphical representation of a graph. So when you look at all the gray lines, all the grayed out lines, that is actually a graph. Okay, you can see there are cycles. When you look at all the gray lines, the red part is representing a spanning tree. So if you pick out any node, any vertex, if you pick out any vertex, it can serve as a root. And with considering that as a root, you can reach every other vertex in this graph. And the red line is always going to be a tree. There's only one way to get to a particular vertex using the red lines. Are we doing okay so far with this concept? Okay, you have a graph, but if you take a subset of all the edges, and if you can somehow use that particular subset of edges and still connect all of the vertices together, it is called a spanning tree. Any questions about the concept? Looking at this picture, I think it gives you a pretty good idea of what a spanning tree is. The other way to describe this is, can anyone find a particular vertex that was connected using the gray lines, but the red lines failed to reach it? There's none, right? So that is the other way to look at a spanning tree, is it has to go over all of the vertices that were originally connected by the gray lines or in the graph. Okay, why is it important? One application is network design. So if you have a network that looks like this, it might be really robust, but at the same time, it is costly because you have a lot of redundant connections between the vertices. So if you want to minimize the cost of a particular network, probably at the cost of reliability, you can use a spanning tree and just say that, okay, I only need connections between these vertices, and that will save me a lot of money because I don't have to run cables like the gray lines are. Okay. Are there any questions about that concept? No concepts? Okay. Approximation algorithms for NP-complete problems, indirect applications. So these are just examples of, this one is kind of interesting. I have not really looked into this, which is how do you do facial recognition using spanning tree as an algorithm. Okay, that one I have not looked into, but apparently this is also useful. Right, so getting back to my own notes here. So what if a set of edges is in every alternative spanning tree of a graph? Okay, so let's go back to that picture that is up here. Okay. The red line is not representing the only way to look at this whole thing as a graph. I can spot a few places where I can quite easily change the configuration, and it will still be a spanning tree. It is not it may not be a minimum spanning tree, but it is still a spanning tree. I'll just give you an example. I can go here, cut out this edge here, and then reconnect that edge over here. That will still maintain the property of a tree. It may not be a minimum spanning tree anymore, which means when you add up the sum of all the edges, that may not be the minimum anymore, but it will still be a spanning tree. Is that okay?
So if you take out that vertex,
No, I'm not taking out a vertex. I'm just replacing an edge with another edge. Okay, look at this. Look at it this way. Let me magnify this one a little bit more so we can see closer. So what I'm saying is, I can take out this edge here, and then add another edge here. So I erase this red edge, turn it back into gray, and then I turn this gray edge into red. That will still be a spanning tree. So every single vertex is still reachable, and then the red line will still be a tree. So that means, given a particular graph, there may be multiple alternative spanning trees. Now, there may be only one that is the minimum, but there are multiple alternative spanning trees. So now the question is, what if you look at all of the spanning trees and they all overlap at certain edges? What does that really mean to you? What makes that edge special now? Let me see if there's one in this graph. I don't think this graph has one. Well, it does, but it's kind of a trivial case. This edge here. Every single alternative spanning tree must include that edge. Okay? So what happens when I remove that edge? There's no way to get to at least one vertex. Okay? I would have disconnected one vertex from the rest of the graph. So that means it is on a critical path. Okay? That edge is now on a critical path, which means it is the only way to go from certain vertices to other vertices. Some graphs have no critical paths. Okay, the easiest way to look at a graph that has no critical path is a triangle. This is vertex A, vertex B, vertex C, and we'll use it as a non-directed graph. So these edges are bidirectional. You can erase any edge, okay, any single edge, and all three vertices will still be reachable within each other. Does that make any sense? Okay. But when you have only two edges left, then both of them are on the critical path. Because if you take out any one of these remaining edges, at least one vertex will be disconnected from the rest. So that's the whole concept that I wanted to express in my statement here. So a critical path is a path from a vertex to another vertex where the removal of any edge will disconnect these two vertices. In other words, there are no alternative paths. The analysis of critical paths is important for tasks such as scheduling. Okay, so why do you think, when you look at scheduling, like a graph or as a tree, why do you think it is important to understand critical paths? critical path actually has a different meaning in scheduling, but it's kind of has a similar taste to it, but it's not exactly the same. What is a critical path when you are scheduling for a job to be done? Hmm?
It's a bottleneck.
It's the bottleneck. Okay. So what is a bottleneck when it comes to schedule?
That's where all the jobs get stuck before processing to the next step. So if you have like 10 tasks to run,
Right.
they're gonna have to wait for that critical path to be ready to go to the next one.
Which also means if you have any delay with that, with any task within the critical path, it will delay the entire project. As opposed to a task that is not on the critical path, you can delay one of those other tasks. It may not delay the entire project. Okay, very good. And also, when you talk about routing, it is also important to understand what is a critical path or what the critical path is when you're dealing with routing. Think about the power grid, okay? If the power grid has certain critical paths, what do you think should happen to that critical path? From the national security standpoint. So let's say somebody actually ran an analysis, okay, of the power grid, and they say, well, I'm just using this as an example, okay? So the power line from here to Davis turned out to be, a critical path, okay? There are no alternatives, everything has to go through that. That'd be probably not true, but I'm just using it as an example. So what do you think should happen to that particular critical path? You have to make it extra safe, exactly. So you have to, send extra patrol airplanes and all kinds of other security measures to make sure nothing happens to the power line from here to Davis. Because if anything happens, then the rest from Davis and to the east, to the west of it, will get power outage. Okay, so that's why it is important to understand where are the critical paths. Would you apply minimum spanning tree or any type of spanning tree on the power grid to save money? that would not be wise. Yep. Because any tree. Oh, here's the other thing. When you look at the tree, how many edges in the tree are in a critical path? One. Think about the definition of a tree, and then think about what a critical path is. Okay, how many edges in the tree is in a critical path? All of them. Yep, that is the answer. Okay, if you have a quote-unquote tree, and you can remove one edge, and the rest will still remain connected, it is not a tree to begin with. That's by the very definition of a tree. All right. So I think we got all of the notes, all of the concepts covered. So at this point, I'm going to move on to the practice exam, or some of the questions that the kind of questions I would say, the kind of questions that you will encounter in the final exam. All right. So this is the first one, which will probably take the longest time. Because this time, instead of using Dijkstra's algorithm, I want you to use the A-star algorithm to find the shortest path using the following definitions. So this time, I'm saving you some time because I'm defining the edges. I'm using a graphical representation of a graph instead of a text representation. So this time is a little bit easier. So the way to do this is I'm going to draw the picture on the whiteboard, so I can actually update, and you can see how the notes are getting updated. Okay. All right, so we have a directed graph, which has A, B, C, D, and E. And then we have all these edges. And you can see that we have one edge going from, okay, this is 5. The other way is 1. This is 10. That is 5. This one is 5. 6, and then we have a 20 going in this direction. That's a 25. That is, uh-oh, I forgot to label one. Let's see. I forgot to label one of them. Okay, so so let me see. Okay, there's a particular way to assign the value, so I cannot make it. Okay, that's a 9, 5. Let's make it a 2. Okay, here we go. All right. So now we have a directed graph, with cost to each edge. But on top of giving you this information, in order to use the A-star algorithm, I need to give you one extra function, which is the heuristic function. The heuristic function is basically just a rule of thumb, an underestimate of the actual distance from a particular vertex to the destination, to one of the destination vertices. So I'm defining h of A, which is an underestimate of the distance from vertex A to vertex E, which is my destination. I'm giving you and say, oh, if you just ask me, and I'm not going to go through this algorithm to find out the actual distance from A to the destination, I'll just throw a number at you and go like, well, it's about 12, okay? And the property of a heuristic only has to be an underestimate, okay? It only has to be less than the actual shortest path distance. Yep.
Oh, I think you switched the A and the B's.
I switched A and
5 and 1. I think you should be that way around.
No, I did not. I switched the direction of the arrows too.
Oh, gotcha.
So it's still okay. All right. Are there any questions about what a heuristic function is? No questions? Okay. So it's just an estimate. It usually can be computed really, really quickly. So in the following space, obviously, there's no space here, but in the exam, I will leave you enough space to clearly indicate the update of these items from the algorithm itself. Okay. So it might be helpful to print out the algorithms, or I can just include it into the question. All right, so let's go ahead and take a look at the algorithm itself. Now remember, we are not inventing algorithms in this class. We are simply following algorithms that have been written already. So we are now talking about the A-star algorithm. Let's go ahead and take a look at it. Now, before we get into the actual useful part of this note here, okay, I want to go to another page first. This one will not be in the final exam, by the way, but I do want to point out one thing that is kind of important. Prim's algorithm is an algorithm where you can find the minimum spanning tree in the graph. Okay, that is the purpose of Prim's algorithm. We're not going to talk about this algorithm. We'll talk about the concept of a spanning tree, but not Prim's algorithm. So I'm not going to look into the details of the algorithm, but instead, I'm just going to give you let you read about the history of this particular algorithm. So let's go ahead and look at this part here. This algorithm was originally developed in 1930 by a Czech mathematician, and then later on independently by Prim in 1957. And then it is once again rediscovered by Dijkstra in 1959. What is that telling you? These people did not use Wikipedia, right? If I'm trying to find the minimum spanning tree, the first thing I would do is do Google search for it, and then Wikipedia would be the first entry, and I just read about it, right? So it is apparently the second person, Prim, and the third person, who's Dijkstra, did not really use a search engine or Wikipedia when they were thinking about, hey, it would be kind of cool to solve this problem. Let me think about how to solve this problem. And they just sat down and and actually used energy to solve the problem instead of searching for it. What is the problem of my argument here? Well, where was the internet in 1957? It's not. There's no internet, right? So the first person who discovered this particular algorithm, Jarnik, What do you think he did with this algorithm? He probably worked it out, published it in some obscure, journal, and that's the end of it, right? And how many journals do you think, people publish all over the world that is related to mathematics or computer science? A whole lot, okay? And even sending physical mail at that time in 1930 is expensive, right? Printing is expensive, sending physical mail is expensive, and then there's the World War, okay? What happens, in the World War with, journals and papers and stuff like that? Some of them get destroyed, some of them get bombed, or burnt down and stuff like that. So that means, by today's standard, nobody's going to do something like this. No algorithm is going to be rediscovered because people have search engines. I just want to point this out so that when you get a job and you have to solve a problem that seems to be, well, that seems kind of difficult, but it also seems like this kind of problem has many other applications compared to what you are really just trying to solve. The first thing you need to do is to do a research. Google helps, okay, but sometimes you might need to actually go to a library to do it. And do a research and see if somebody else has already found an algorithm to solve the problem. In some cases, the problem may be solved already by multiple algorithms. Then you have to look at all the alternative algorithms and compare them and see which one you want to use. How would you compare two algorithms that solve the same problem? We talked about this too. We talked about this in the class right before spring break, where I had a slight technical difficulty and could not. I recorded the class, but then I recorded over it. That's the one lecture that we lost on YouTube. What did we talk about?
Big O notation. Big O notation.
Big O notation. Okay, so Big O notation can be applied to many things, but in that particular class, we applied it to only one thing. So did we apply it to the amount of space used by a certain algorithm, or did we apply it to the time used by a particular algorithm? The time. So we talked about time complexity, right? So when you look at algorithms that can solve exactly the same problem or alternatives to solve the same problem, you have to look at the time complexity. So I just want to point this out because we have talked about this algorithm. We talked about this topic already. So sorting algorithm is nothing new. I mean, there are obviously many of these algorithms. And if you want to take a list here, even efficient sorts, okay? There are multiple efficient sorts. There's merge sort, there's heap sort, and there's quick sort. All three are considered really efficient. So what you need to do when you find multiple algorithms to solve the same problem is to look at the complexity. The time complexity, and if it does make sense, space complexity. How much space is it going to use in order to solve the problem? So those are the things that you kind of have to remember to do when you are finding when you're trying to locate an algorithm to solve a problem. Okay. Does anyone feel that you're kind of lucky that you're in the right century where Google, Wikipedia, and all of these resources are here already? Well, I do, because I kind of crossed over from the era before the internet was around, okay? And there's no easy way to locate anything. I have to go to the physical science library at UC Davis to do any research. And then you have to read a lot of books. There's no search, right? When you're dealing with a physical book, you actually have to read it, okay, to find out, okay, what is this about? Okay, the title seems to be related, but you have to actually read the content. But today, you have the internet, you have Google, and Google has extended its indexing ability to also index books, okay? Not just websites, but even printed books are now indexed by Google. So you guys have that really one extra, technological help, in your career, and I just think that it's really nice to have all these resources. All right. So getting back to the final exam here, so we are going to apply not Dijkstra's algorithm, but A star. I can get to it from here too, because all the search algorithms belong to the same family, and it is all indexed here. So A star is right here. The A star algorithm, in terms of time complexity, the worst case performance is big O of E. Yep.
What did they use it for in 1930?
That is a really good. That's a really good question. You know, some people think of, you know, well, 1930 is before the computer, right? It's before the end of World War II. You know, where the first practical electronic computer was invented. So you are absolutely right. You know, that's a very good question. Well, people think of, you know, theoretical stuff for, you know, to solve problems, even though there are no tools to do it at the time. Okay.
You did everything by hand.
Yeah.
Having practical use.
Exactly. So some people think of all these theoretical things and go like, well, what if I have a problem like this? And how am I going to solve that problem? The guy thought of, hey, we can do it this way, even though there were no computers. You can apply it by hand, which is actually still useful. Okay, because if you do have a problem of finding the minimum spanning tree and you don't have a computer, doing it by hand is not bad. Having a known method to do it is what is important. But that's a really good question. That's a very insightful question. Is, you know, like in year 1930 there were no computers, so the concept of algorithm is not even applied to computers. Okay, that really says something about, you know, mathematics and the algorithms, you know, because it's more math than computer science.
What's the question? What's the question?
The question was what was that guy doing with the minimum spanning tree algorithm, you know, otherwise known as Prim's algorithm, in 1930.
Oh, that's right.
Now, if you ask the question and say, why is Google interested in that algorithm? Oh, I can think of like 20 ways why Google might be interested in that, you know, algorithm. But in year 1930, there's no application because there were no computers. Algorithms were only for people to follow. There were no computers to program to run an algorithm. Okay, and I think that really is the true differentiation between someone who writes programs, a developer, from a scientist, from a computer scientist, which is more like a mathematician than an actual scientist. Right. So getting back to the A star algorithm here. It has a worst case performance of big O of the cardinality of edges. So that means, you know, if you have a lot of edges, it can take a long time to run. If you don't have a lot of edges, it will not take a long time to run. The bottom line is each edge will only be evaluated exactly once. Okay, and that's why it is big O of the cardinality of E. But we're going to skip all kinds of stuff. Well, maybe not all. The other part that is kind of noteworthy about this one here is it's an extension of Dijkstra's algorithm in 1959. But when you look at the organization that these three people belong to, it is SRI, or the Stanford Research Institute. Does anyone know, you know, what is the SRI? What does it do? Yeah. Okay. I think he's looking it up right now on the phone. So what does SRI, you know, do?
SRI.
Yep. Okay, let's find out. Okay. Well, because some of you may end up working there. I mean, if you don't know about, you know, these, you know, SRI or Stanford Research Institute International. I know the answer already, but I want to bring you to the website just so that you know what it is. About us, overview, here we go. Okay. Okay, SRI is a non-profit independent research center serving government and industry. We work on some of the world's most important problems, collaborating across technical disciplines, blah, 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 blah. So basically it is a bridge, okay? It's a bridge from research labs, graduate schools, and whatnot to industry, okay? How do we apply all of these really cool stuff that people come up with in the labs, okay? I can think of a few examples that might have gone through SRI. Google cars, okay? You know, the cars that go around to take the street view pictures, okay? That is actually based on the research of autonomous vehicles from Stanford. Stanford went into the urban challenge competitions, and basically they were competing with a lot of other top-end schools. So it's a research thing, and it might cost a lot of money to make a vehicle like that. In the commercial world, they cannot spend like $20 million on a single vehicle. Okay, that works most of the time. So the bridge to bridge the research work to a practical use, is important, because otherwise, all the research work is really just, oh, it's kind of nice that you can do it, but we don't find any use of it. So SRI is an organization that bridges that particular gap, going from academia to industry. Why would that be important to you? Come on, quick, Tag, just finish up this semester so I can get back to game programming, right? Well, they also do a lot of security research. Okay, security is a big thing too. The only reason why I knew about this one is because the graduate school of UC Davis actually had the ex-director, prior director of SRI. And what happens is, so the computer security program as a graduate program at UC Davis in the computer science department is actually really strong because of that tight connection with the SRI. So what happens when you are a graduate student in that program as a computer security graduate student? And you prove to your professor that, yep, I can do independent thinking, I can do problem solving, I can publish papers, and do all kinds of stuff like that. What do you think happens when you're done with your dissertation or your master's thesis?
That job you're probably hired is fast.
Exactly. There will be people, waiting for you to graduate and say, we have a job for you already, so hurry up and graduate. Okay? That is why it is important, okay? Because you want to know about these connections, because just getting an advanced degree does not mean a whole lot, okay? Unless it is connected to industry. And the SRI is one of those organizations where they connect research to actual applications in industry. Is anyone transferring to Davis? Or okay, so when you transfer to Davis as an undergraduate, it's not as relevant to you, okay? Because these are mostly for graduate students. But when you consider graduate school, you definitely want to look at whether their programs relate to industry, whether they have a tight connection with industry. Because if you don't, a lot of times yeah, you can get a degree, but what does it mean? On the other hand, if your professors are also connected to SRI or some other organizations of the same kind, they can you can actually get hired pretty quickly. My roommate in graduate school, he was like that. He's still working at SRI, but he was hired basically before he finished up his PhD. It's just that these organizations will ask professors and say, hey, which ones of your graduate students would you recommend to work at my place? Okay, they would constantly get requests like that. So, not 100% related to discrete math, but I think at some point it's going to relate to what you plan to do in the future. All right, so getting back to Wikipedia. All right, so now we get to the actual useful stuff here. This is the algorithm. Yeah, I know it looks like a big mess. But it's actually not too bad. Okay, so we'll go ahead and analyze this algorithm and apply it to this particular graph at the same time. A star is not recursive. Okay, it is one of the few algorithms that is not recursive because it's not really easy to make it recursive. You cannot break it up into a subproblem, and solve the subproblems and combine the solution of the subproblems. So in this particular case, we have to keep track of two sets. One is called closed, and the other one is open. On top of that, we have two arrays. One array is called G Score, and the other array is called F Score. G Score is basically saying, how much does it cost to go from the start vertex to this point. Okay, so compared to where I'm standing, I'm saying, okay, what is the cost of the shortest path known to me so far from the starting point to here? Is that okay? Does everybody understand what is G score? F score, on the other hand, is saying, okay, what is the estimate from here of the entire path going through me to the destination, to the final, to the goal vertex? Is that okay? Are there any questions about what is the G score and what is the F score? No questions? Okay, it is kind of commented here as well. So if you read the comment, it kind of describes what it is. So let me just kind of scroll through here. Closed set is the set of nodes already evaluated. It's fully evaluated, and it should not have to be revisited again. Open set is the set of tentative nodes to be evaluated. In other words, those are the nodes that seem promising to be on the shortest path. Is that okay? All right. Well, we'll keep going from here. Came from is the map of navigated nodes. It keeps track of a way so it can go backwards. Okay. G score is the cost from the start vertex along the best path to a particular vertex. F score is basically the G score plus the heuristic estimate, which is basically saying, if you go through me, okay, this is the current estimate of how much it will cost you to go from the start vertex to the goal vertex. Are we still doing okay so far with what each component is doing? All right. So what we'll do is we'll track a table, because I want to show you the algorithm at the same time. I'm going to use the whiteboard to do the tracing. Okay, so I know this time is not going to be, this part is not going to be captured by the video, but at least the audio portion will be. Okay, so we want to keep track of open or closed, which is a set. Open is a set. We want to keep track of the updates to G score and also F score. So G score and F score. Those are arrays, and also came from. All of these will be defined, as the algorithm runs. In this case, because we only have 5 vertices, it's not going to take up that much time. Even though it looks really complex with edges flying everywhere, many of these edges will not be explored because it doesn't make sense to explore those edges. So as we work on the algorithm, we'll see. So you start with the initialization. So the first line here says the closed set is supposed to be empty. In other words, when we first start off, nothing is evaluated. Well, that makes sense because I haven't even started any work yet. Okay. The open set is the start vertex. That makes sense as well because the only one thing that I know has to be on the shortest path is the start vertex. That has to be on the path. So the open set only has, in this case, A, because vertex A is the starting point of what I'm trying to do. Came from is an empty map, which means there's nothing to remember at this point. So I'm just going to say this is empty. Or just say nil. The next line is right here. It says G score of the start vertex is a 0. In other words, it costs me nothing to go from the start vertex to where I am. Does that make sense that it will cost you nothing to go from vertex A to vertex A?
Yes.
Okay, I sure hope so. So I'm just going to use this representation to say that G score bracket A equals to 0. 0 here. Okay, so F score, on the other hand, is an estimate of saying, okay, if we have to go through me, being vertex A, what is the current estimate of how much it will cost me to get to the goal? Okay, in this case, the heuristic cost estimate is done by the H function that we just mentioned a little bit earlier. So if you go to the bottom part here, the answer is 12. So F score is going to be 0 plus 12, which is just 12, the one for vertex A. Is that okay? All right. So we are now done with the initialization, and we can now move on to So let me bring the algorithm right next to this one, so this way it's not easy to get lost. While open set is not empty, is open set empty at this point? No, it has one single element in it, right? So we have to get into the loop. So now we say, okay, let's set current as the vertex in the open set that has the lowest F-score value so far. Yep.
So where did the 12 come from?
Say again?
Where did the 12 come from?
The 12 here, it comes from the current, the cost of the known shortest path to vertex A plus the heuristic of vertex A.
Oh.
In other words, the heuristic estimate from vertex A to the goal state, the goal vertex, which is E in this case. Okay. All right. So we are now moving on to the highlighted line. The current node is the node in open set having the lowest F-score value. Well, if you look at the open set, how many elements do we have? Well, so A has to be our current. Yep, go ahead.
Do you have to do the curly brackets in the A for each one of those?
For these, yes, because these are arrays, so I'm just using a shorthand here to basically say this is G score bracket A equals to 0. Okay, so the current, so that we move on to the next line. Current is vertex A. Yep.
What did it say under came from?
Nil.
No?
Nil, which means we don't have anything here yet. So there's no mapping yet at this point. Okay. If current is goal, you return reconstruct path. Reconstruct path, by the way, is another subroutine down here. Okay. But right now we are not too concerned about it because is vertex A the goal? Are we trying to get to vertex A? No, we are trying to get to vertex E. So the condition of this conditional statement is false. We're not going to do anything here. And this code is, it also uses a return statement in the middle of a conditional statement in the middle of a loop, which I strongly discourage. I just want to point it out because whenever and wherever it is appropriate, I want to point out certain programming styles that I do not particularly like. Okay, because this. Why do you think this is not a good idea?
Because then that's where your loop will end.
Sorry?
That's where your whole program might end and return to whatever called it.
Right. This is going to return from the entire subroutine, but why is that not? Why do you think I think it is not such a good idea?
You ran out of memory?
Hmm?
You ran out of memory?
No. It's actually very efficient. Okay, if anything, this is a very efficient way of doing things because you're not going to go through any extra code. When you think I'm done, I'm returning, even though you are in a conditional statement that is inside a loop. But why is it not necessarily a good idea?
How do you really know you're done?
Well, the condition. If current equals goal is the condition. So if current equals goal, I'm out of here.
But if the code is not perfect, finding the error is going to be
Analyzing the code. Exactly. Analyzing the code can be difficult because now you have multiple ways to get out, quote unquote, get out of the loop. Because to get out of the function is to get out of the loop, right? So when you analyze the code and you say, okay, by the time I get out of this loop to return failure at the end, open set has to be empty. So you would think that that's the only reason that you can get out. But no, there's a second reason you can get out, which is going through a return statement inside a conditional statement inside the loop. Now, there's another one that is even worse. Well, I wouldn't say even worse, but it's kind of bad too, is to have a continue inside a conditional statement that is inside a for loop. But, that's not exactly a discrete math, type of topic. But whenever I find something like this, I just go like, Okay, next thing we do is we move current from open set. Well, let's go ahead and log it, right? So we just say, open is now empty. Because I just removed the only thing that is in it. And then the next statement says, we have to add current to closed set. So now the closed set has the vertex A because we're just basically moving it from one set to the other set. Okay, now we get to the fun stuff because here is a for loop. This is not a typical C++ for loop. This is it's more like a scripting language where you can say for each neighbor in the neighbor set. All right, so how many nodes or how many vertices are neighbors of A? Just look at the picture here.
B, C, D.
There are 3 of them, right? So there's B, there's D, and there's C. They're all quote-unquote neighbors because there are edges going from A to B, A to D, and also A to C. So now you kind of have to mentally keep track of it because I do not need you to do it here. So you kind of have to mentally keep track of, okay, there are 3 neighbors to consider. Just pick one, okay? Now, there's no particular order in this case. It doesn't say, for each neighbor and pick the neighbor with the least cost or anything like that. So you can really just randomly pick one. Which one do you want to pick out of A, B, D, and C?
B. You know, it's makes sense to remember.
You want to pick B? Okay, let's pick B then. So neighbor is B in this case. So the next thing you have to do is to say, is neighbor in the closed set already? In other words, have we evaluated vertex B already? And this is just a loop going back to something that I have seen already. Nope, okay. So that means we are not going to do the continue, and instead we'll do the next statement. So now you have to keep track of this, what we call tentative G score, which is basically the G score of the current node, which is A, plus the distance between A and B in this case. Okay? And what would be the tentative G score? Now, if you want to trace this, with more, and keep track of more things, so you don't have to keep track of stuff in your mind, you might want to write it down too. Okay, so you might want to write down who is the current neighbor, and what is the tentative G score. Okay, because this way it's easier for you to keep track of everything. The current is A, that's coming from this step here, the first step. The current neighbor that we're evaluating is B, and the tentative G score is what? How do we compute it? Okay, it is how much it cost to get to A, which is 0, and how much would it cost me to go from A to B? It's 5 units. Okay, so the tentative G score is 5. And then now we look at this whole conditional statement here and ask, is the neighbor not in the open set? The neighbor is B. Is B in the open set at this point? What is the open set, by the way, at this point? It's an empty set. Okay, so B cannot be in the empty set. So the first condition is true. This is a disjunction. We're going to go into the conditional statement because it's an or. So if one statement is true, or if one side is true, we go into the statement. So we now say came from neighbor equals to current. So the way we denote that is to go to came from, and we basically say neighbor is B, and then we say that is A. That means in the currently known best path, okay, we go to vertex B from A. That's basically what it's saying. It's trying to remember a way to go back to the start vertex. Okay. Next thing we do is we look at G score neighbor and update it. Okay. So we update G score neighbor is B, by the way, to the tentative G score. So we look at G score and we basically say the G score of B, which is representing the cost of the shortest known path, the known shortest path to vertex B to be 5. That makes sense, right? Because we just went from here to here. 5 is good. And we update the F score, which is an estimate. Okay, now F score is actually the most important part of the A-star algorithm because Dijkstra's algorithm does not make use of any heuristic. Okay, this one does. So the F score is reflecting the shortest path from the start state A going through me, vertex B, to the goal vertex. My best estimate at this point is that number. That number is going to be 5 plus the heuristic of B. And if you look up the table, the heuristic of B is 10. Okay? So it's 5 plus 10, which is 15. So at this time, I update F score and say the estimate of going through B to the goal state is 15. Are we still doing okay so far?
It's supposed to be like unaligned. Is it supposed to be like that aligned, or
Is it like
Is this supposed to be not aligned?
not aligned? This is the next line. Well, you can put it to the previous line. It's in the same iteration. So whether they are off a little bit or not, it's not important. But it is a step after this one, so that's why I use the next line. Yep.
Yeah, F score neighbor. What is neighbor? How do you know that neighbor is referring to A and not?
Neighbor is referring to B because I just remember that. Because what the neighbor comes from, I don't want to change the highlight because we are actually focusing on this line. But
Oh, I
neighbor
see.
comes from here, and we evaluated. We pick the first neighbor to be B, even though there are 3 neighbors. We pick this one to be the first one to be evaluated. So the highlighted line, we move from this line to the next one, which asks, is neighbor in the open set at this point? The answer is no. B is not in the open set. So now it says, okay, let's add it to the open set so that this becomes the next candidate to evaluate. So now we have B being in the open set. Are we still doing okay so far with tracing this algorithm? We'll do another iteration, and then we'll just kind of say, okay, I'm going to let you guys do this part, okay? But it really is just tediously following the algorithm to keep track of where we are, what are the values, and so on. Okay, after this, we are going back to the beginning of the loop, which says, is the open set empty at this point? Well, it was empty at some point, but then we added B to it. So right now it is not empty. So we go back to the second line of this loop here and basically say, let's pick a node in the open set that has the lowest F score value. Well, I don't have to pick anything because there's only one member in the open set. So now we just say the current is now B. And well, let's see if we can shortcut stuff here a little bit and make it quicker. B is not the goal, okay, so we'll ignore the return here. Remove it from the open set, okay, fine. Take it out of the open set, and the next line says add it to the closed set. So the closed set now has A and B in it, right? And then what we do is for each neighbor in neighbor nodes of the current, but current is now B, so we want to look at all the neighbors of B at this point, okay? If you look at the neighbors of B, how many neighbors does it have? It has, well, it has 4 neighbors. It has 1, 2, 3, and 4. It does have 4 neighbors. Okay. So which one do you want to pick? Because there's no prioritization as far as picking a neighbor to be considered. Let's pick the one that seems to be the most promising. We want to get to E. It's already there. Let's pick it. Okay? No, there's nothing in the pseudocode that says you cannot pick E at this point, right? So the question now is, will it decide that this is the shortest path accidentally and ignore the actual shorter path? Okay, so let's go ahead and do it and find out what happens. So we'll pick the neighbor of B. We'll pick the first neighbor to be evaluated to be E. Okay. Move on to the next line, which is this line here. Neighbor is not in the closed set, right? E has not been explored yet. Okay, fine. We'll now calculate the tentative G score of E. So what this...
I think for the last loop, when we check the current I, we didn't check the neighbor or the neighbor I yet.
You're right. We finished this one here. We did not go back to the we did not go back to the for loop. You're right. Okay, I forgot about that. That means we have to. Sorry about this. You guys have to cross out stuff in on your paper. Okay, so B is in the open set. Yep, it will still be in the open set because we have not removed it yet. There we go. So he was right. We have to go back to this point here because there are two additional neighbors to consider. We evaluated B as a neighbor of A already. Now we can evaluate D as a neighbor. So we have to go through the neighbor here and say, okay, this time we're going to use D. And D is not in the closed set. We have not evaluated D yet. So now we have to calculate the tentative G score of node D, or vertex D. Okay, what should that be? Current will still be A at this point. And the known best, the cost of the shortest path to A still has a cost of 0 because we are at the origin, plus the distance between A and D. The distance between A and D is 20. Okay, so the actual tentative G score is going to be 20. Okay. If neighbor is not in open set, well, is D, which is our current neighbor, being considered in the open set? Nope. Okay, so that means we can move forward into the conditional statement. Came from neighbor is current. So we go to came from, and then we say we go from A to D, which is basically saying the current shortest path to D is coming from A. That's what it's saying. The next statement is updating the G score of the neighbor, which is our D here. So we update the G score of D to be the tentative G score, which is already calculated, which is 20. And then we also have to update the F score. The F score is G score, which is 20, plus the heuristic cost function of vertex D. So we have to look up on the other side. The heuristic function applied to D is only 3. So 20 plus 3 is 23, and this one gets 23. If neighbor is not in open set, add it to the open set. So the open set is now B and D. Is that okay so far? Okay, I'm just going to check whether you understand what these columns actually represent. What does that mean? What is the meaning of F underscore score? Wow, that's okay. F underscore score bracket D equals to 23. What does that mean?
The estimated distance between A to B
To E is 23, right? And the property of H is an underestimate. Okay, so H is always underestimating the actual distance. And by the way, why is the F underscore score useful? Why is that array useful? Where the only part that makes use of that particular array is where? We're putting values into that array here, but where is it used? The only time it is used is here. It helps us prioritize which vertex in the open set we'll explore next. Okay, and that really is the key of the A-star algorithm. This is actually where the heuristic is being used, is to prioritize and say, okay, with all the potential vertices that I can explore at this point, which one looks the most promising? That is what it's asking. So it will explore the one that is the most promising and see whether see where it goes, and then it will go from there and see what is the next most promising node is. Is that okay so far? Yep.
Wouldn't it have to go through all possibilities anyway?
Nope. No.
It can cut short.
It can cut short. There can be vertices, depending on the graph, there can be vertices where it is guaranteed not to be on the shortest path, and it won't even be it will not even appear in the open set even once. When you look at the okay, I'm just gonna scroll this one up. When you look at the graphical A star. No, there is one somewhere. Right there. Okay, I can't really pause it. This is not an actual video, but when you look at the one with solid color, not the dark blue ones. The dark blue ones are basically indicating a barrier. Okay, so the nodes are not connected to the other side for the dark blue ones. The red ones and the orange ones, those are the ones that are being evaluated. The ones with the hollow blue ones, those are the ones in the open set. The ones with solid color other than the dark blue, those are the ones in the closed set. And the destination is over here. And you can see that there are nodes or there are vertices on this graph that are unexplored, even when it finds the shortest path to the destination, to the goal vertex. Okay, so that's one of the properties of the A-star algorithm. Is if there are vertices that are completely unreasonable, they won't even get considered. It's kind of like looking at a map of the United States, and I'm trying to find the shortest route from ARC to downtown Sacramento. Okay, I'm pretty sure there are interesting places in Memphis. but Memphis will not even be even put into the open set even once. Because the vertices leading to Memphis, those will not appear onto the open set even once. So that's the nature of an efficient search algorithm. Is it will only examine and evaluate vertices that look promising. But that also depends on the heuristic function, because the heuristic function, when you look at a map, okay, so when you look at a map, this is an approximation of the continental USA. Okay, looks about right. Okay, so when you look at a map, what would be a good heuristic to use? Okay, I'm trying to go, let's say, from here to here. Okay, what would be a good heuristic to use? The heuristic function has to be something that is easy to evaluate, in terms of time, and it has to be an underestimate of the actual distance.
Straight line.
The straight line distance, very good. Okay, so when you look at the straight line distance, this is the this is the heuristic from the start to the goal, right? Because short of wormhole technology and other type of space warping technology, there's no way you can go from the start vertex to the goal vertex with any less distance than the straight line distance. So that makes it a very good heuristic function because it is always underestimated. But not only is it always underestimating, if I go look at New York City over here, the heuristic function of New York City to my goal is going to be a lot more than going from here to here. So that means I would be exploring a lot of vertices around the start vertex, but this will never be considered. Does that make any sense? And that has to do with the prioritization, based on the heuristic function. Well, a part of it, but because of the heuristics, anything that leads to this far away point will not be evaluated. All right, so we are almost done with the algorithm. Let's go ahead and finish at least the for loop. In the final exam, I'm going to give you something that is easier to deal with. It's not going to take up as much time. I think I just got past the algorithm itself. Right there we go. All right, so we are getting back to the for loop. We are not done with the for loop yet. Now we have to evaluate the third neighbor of A, which is C. So we're going to do the same thing. The neighbor is going to be C, and we'll go through all this code here. C is not in the closed set, so that's good. We move on. The tentative G score is going to be 0. Whoops. Tentative G score is over here. It is going to be, I know some of you cannot see it. Sorry? Oh, okay. It's going to be 0 plus the cost going from A to C, which is 6. Okay, so there's a unit of 6 units here. And then we look at this statement here. C is not in the open set, so that means we we'll continue with this one here. We basically go to came from and say, we go to vertex C from vertex A. That's what it's saying. The G score is going to be just the tentative G score here. So the G score is going to be 6. And then the F score, which is the estimate of going through C to the goal vertex, is going to be 6 plus the heuristic function of C, which is 11. 11 plus 6, which is 17. Okay. And then we add it to the open set. So the open set now has B, C, and D as elements. Are we okay so far? So when you look at the meaning of the closed set and the meaning of the open set, the meaning of an element being in the closed set simply means that we are done with those. Okay, we have evaluated that particular vertex already. We don't have to go back and reevaluate it. When someone is in the open set, it means it looks promising. Maybe we should take a look at it. Okay, so you keep track of a set of vertices in the open set. Now we are actually done with the for loop. Okay, because we have evaluated every single neighbor of vertex A at this point. So we go back to the beginning of the while loop. The open set is definitely not empty because now it has 3 elements. This is the crucial part. We are going to pick one out of the open set, but not randomly, because it is going to be based on the F score value, which is the estimate of, okay, let's see which one is the most promising, because I want to look at the estimated cost going through this vertex to the goal vertex. So in this case, we have B having a value, over here. B has a value of 15, D has a value of 23, C has a value of 17. The most promising is B. So now we pick B as the next current, and then we expand from B. Are there any questions about this step? Because I won't have enough time today to finish the entire algorithm, and I will think about how you can update the map, in the exam, because doing it this way, seems to be a lot. It's easy and hard at the same time. It's hard because there's a lot of stuff that you have to write, but it's easy because it keeps track of everything, so you don't have to keep track of stuff in your mind. So it's both easy and hard. I have to kind of think about, how to do this in the exam, so it will still be doable within a reasonable amount of time. I will do this myself and finish it up. So I'll give you the solution. So this way you guys have something to hang on to and say, okay, this is the solution to this one. Can anyone guess how I'm going to do that? The tech is just going to do it by hand. No, there's no way I'm going to do this by hand. How do you think I'm going to do this? I'm just going to write a script to do it. Which programming language do you think I'm going to use? Or which one do you think I'm not going to use? I will not use assembly language for sure. I'm not a really good Python programmer, but I know Perl, so I can do it in Perl. Yeah, that's what I'm going to do, is to do it in Perl. So I will give you the solution, and even the Perl script, so you can play with it if you want to. And it should be done, I would say sometime maybe today or tomorrow. If you don't see anything from me today or tomorrow, send me a gentle reminder. Yep.
Have you decided if it's going to be this number?
In the test, there will be another one. So for the homework, it's Dijkstra's algorithm. For the practice exam, it's A-star. So for the final exam, I need A-star. The iterative, deepening A-star. It might be something easier. Or it might be applying this to something else. Well, Vincent is taking a...
Might as well, right?
Might as well. Sorry. Take a picture of Passat too.
wrote it down. I just want to make sure. I have a question, Professor.
Yep.
Remember my exam?